My name is Bruce McCormack, and I'm the president of IRLOGI, and it gives me great pleasure to say that we have got a real expert in AI, machine learning, and all the rest of it in the form of Asma, and she will give, no doubt, a very, very interesting and informative, sorry, what? I'm getting all sorts of messages here. She'll no doubt give a very informative and interesting presentation. Now, I won't introduce Asma, although Asma, for the past 5 or 6 months, you and I have been meeting every week on developing some AI agents. So I know you quite well, but I won't introduce you. I'll leave it up to you to introduce yourself. And other than that, I would just say that we are recording this particular presentation, this particular webinar. We are recording it, and we will make the link available when it's all done through our IRLOGI LinkedIn facility. So I think without further ado, I would like to hand over to you, Asma. Just introduce yourself firstly before you actually present.
Okay, so hi, can everybody hear me, right? You can hear me, Bruce, I assume.
Yeah, absolutely, yep.
Yeah.
Yes, we
so
can.
my name is Asma Slaimi. I have a PhD in computer science, particularly in machine learning. I did master's also in machine learning and PhD in Dublin City University. And I'm currently working as a postdoc researcher in Insight. I mainly work in AI. My focus is actually the environmental science and water level rises in island, flooding, etc. But I do work on other fields such as sports and NLPs and different other domains. And today I am here to give, let's say, a brief presentation for AI and the use of AI for flood prediction and mapping. Do you want me to start sharing? Are we ready to start, Bruce?
Yes, I know there's 1 or 2 people coming, but it's already 4 minutes after the start time. So this is me. I quite like to start as near to the start time as possible. So, yeah. Asma, you mentioned Insight. Could you just, others might not know what Insight is.
Okay. So yeah, Insight is one of the largest research center in Ireland, mainly focuses on the application of machine learning and big data in general in different domains. So for example, I work mostly in kind of, as I mentioned, environmental and sports science, but we are across different domain all over Ireland, and we have 5 sites all over Ireland. We are one of the largest research centers that have PhDs, postdocs, and different projects, European funded projects and industrial funded projects.
Yeah, thanks. Okay, Asma, would you like to get going?
Yes, I'll be sharing my screen now. I have a presentation, and when you start seeing my sharing.
I can see it, yep. AI for flood prediction and mapping.
Yes. So as I mentioned today, I'll be mostly talking about the flooding, the use of AI for both the prediction and the mapping. So I already presented myself, and I think we can go to the next slide. So today, mainly, I will be focusing on in general, why floods are difficult to predict, what kind of data we use, what kind of traditional models. I also have a little bit of light demo. I created a little bit of dashboard to present today, and some key challenging and future direction. And we will conclude this presentation with some of your questions. So to start with, I wanted to start by defining both prediction and flooding. When we talk about floods in general, and we talk about flood prediction, we are actually focusing on anticipating the future flood condition. That means when the flooding is likely to happen, how severe is it expected to be, what are the probability of flooding at a given area. So we are talking about mostly when and how severe and the amount and all of that. So it involves usually time series and spatiotemporal models and a different type of data sets, the rainfall, the river levels, the soil moisture, and different other features. All of these combined in order to forecast the flood-related variable. So a typical output here can be from a flood prediction scenario, the probability of a flooding in a certain area, the water level or the discharge rise or forecasting in a certain area or in a certain river, and the flood severity in a time or in the current time or in a step in the future. So, however, now when we talk about mapping, flood mapping usually focus on identifying the extended flooding area. So if we are talking about a place, you see those kind of maps where it shows that it's red, then it's yellow and it's green. So where is the flooding happening and which area is affected and how far the flood extends on the geographical land. So when we talk about prediction, we're more identifying where it can happen, how severe it can be. But when we talk about mapping, we are talking about if you consider the area where it will happen and the border of that area. So it's usually performed using Earth observation data and satellite data and images. And a typical output here can be a map or a polygon showing the flooded area and the non-flooded area. And I wanted to start by these two definitions because usually flood prediction and flood mapping, they do happen together in order to give the best results, but they do use different input, different models, and they produce different output. So flood prediction is mainly about when and how likely flooding will occur, while flood mapping is actually about where flooding is happening or has already happened. So now this takes us to the next part of this presentation is actually why flood prediction and mapping are hard to perform and why till now we are still seeing a lot of area flooded, and we although with all the advanced of technology that is in the world, we still cannot really anticipate how severe a flood can be. Exactly, let's say we can anticipate, but we cannot anticipate it exactly. So what makes flooding challenging is because it's dynamic in time. Flooding, usually these events, they are very rapid and they involve over time quickly. The second main challenge that makes this task very challenging actually is that it is influenced by the whole architecture and the infrastructure of the area. So the drainage pattern, the urban future, and all of these they create a spatial complexity for this event. The third, it kind of affects most of the machine learning and most of the AI actually projects and models and their results, which is the data. The data, although we have a lot of time series data, it's still limited. We're still limited in terms of the observation, the sensors, the labeled example, and all of that. So although, for example, in Ireland, we have almost around 365 water level sensor within all the river, but still with all of those sensors implemented, they are not covering all of the parts or all of the different rivers, for example, which makes it very hard to anticipate how a river can handle actually from the water flowing into it, among many other data limitations. The uncertainty. So flood prediction and mapping are always, they do have a part of uncertainty in their results, which is due to model limitation, the measurement, as we mentioned earlier, the data limitation, and the fact that it evolves very quickly in time. So the other big part that I really want to mention here is the goal, which why we are building or why we are performing this particular project related to flood mapping or prediction. So the goal in here is always to provide actionable intelligence under uncertainty. So we are trying to predict and trying to make scenarios to handle flooding events. So if we take a little bit of a step back and talk a bit about the traditional approach, so flooding, and in the early years and before, we didn't have this kind of technology and AI advancement on all of this. So flooding and these scenarios usually were performed using traditional approach. So the first one is the physical-based approach, which it has a strong physical grounding, and it uses basically the measurement that they are collected, and it follows the natural, how this phenomenon happened naturally. We have the satellite-based mapping, which uses the different satellite imagery and all of that to kind of map the area. And we have the static risks map, which are usually used for planning, and they are not event specific and not time involved. So usually these maps are created after all of these events happened and after all of the kind of the variable of that flood has been collected. Now, if the idea here, or the question that can be asked, where does AI fit in all of that? So AI can complement traditional method by learning patterns from multi-source data and produce fast repeated output. So usually the basic concept of idea of using AI in order to solve one of these problem is trying to understand how the flood event happened and trying to anticipate whether it will happen or not based on different variable. So basically, we're saying if the flood, for example, that happened a few years ago, I think in China in 2003, if we take all of those variables within that event and trying to ingest it to a model, it will be able to anticipate when certain similar variables that happen. For example, when we are having the same extended amount of rain over 24 or 48 hours with a certain intensity in a certain area where the soil absorption is a certain wire X, and we are trying to understand the phenomenon. So AI, it's most valuable when it supports speed, scale, and decision support. So as I mentioned before, in order to be able to perform any AI or to build any AI machine learning model, you need data. Data is the core input or the core element that it will influence your results. So there is different type of data that play a big role in flooding or flooding mapping and prediction. Among them, we have the Earth observation satellites, which we have the SAR, the synthetic amplitude radar. We have the different images that comes from the satellites. We have the terrain data, which is the flow, the drainage network, the landscape, the flood. So, for example, the water doesn't flow the same within an area when it's uphill or downhill, and etc. So all of these are variable to consider when trying to model these or to create the flooding models. So we have the land surface characteristic, which is the soil type, the different land cover, etc. And we have the the sensor-based data, which are the data that comes from different sensors implemented all over different areas, such as the rain, the river level, the discharge, and etc. So if we use all of these data sets, as we mentioned, dependent on the input and dependent on the task, we'll have a different input output to the model. So as we mentioned earlier, flood mapping is all about the where, and flood prediction is about the when and the how much. And so I wanted to mention that these different models are evaluated with different approach. So usually when we create a model, we need to think about how are we evaluating the results coming out of this model. So for example, for the flood mapping, we care about the where. So we, for flood extent mapping, as we said, we care about the where. So we are caring about the boundary accuracy. So we care about the true flood boundaries and how it's shaping, or where these boundaries end and start. So for the flood prediction, however, we are caring about whether it's gonna flood, how much, and when. So we usually use a more oriented evaluation metrics, such as the root mean square error and the mean absolute error. So mainly these are reflecting how correct are we in this prediction, or how much we are far from the reality. Now, as we talked about the different flooding, the prediction, and the mapping, now we need to talk about the methods used to perform these or to create these models for flooding. So there is different approaches in here. As you can see, we have the classical machine learning approach. I want to start with them in this order because for example, the classical machine learning approach, they are usually used as a baseline. So when we talk, for example, about the random forest, I'm not sure if you're all familiar with random forest or not, but a random forest, it shapes your data in the shape of a forest or different trees, and it goes with yes or no and yes or no. For example, if you model it in a simple way, the flooding happened in this area, was it severe? Yes, and there will be an interval and anything. So later on, when we're trying to predict, the model will try to follow that branch till it finds the results. So usually the classical machine learning model provides strong baseline when combined carefully with engineered feature, such as the rain, the land use indicator, and different other attributes. So they are usually efficient, and they usually perform well when the data volume is limited. And that's why we usually use them as a baseline. So random forests are great and XGBoost, but as much as we have data, they slow down, and they are really hard to work with an extended amount of data. So in the second place, we have the conventional neural networks, and in particular emphasis on the U-Net style architecture, which is a kind of neural network which is usually used for image segmentation. So what it does is the architecture, it segments the image to different objects, and we focus on certain object for a certain task. And they are widely used for flood mapping, as you can anticipate, because they kind of used, they are focusing on the image, and they learn special pattern directly from the data, and they are very effective with high resolution flood masks that comes from synthetic radar data SAR or the different satellite image input. So in a third place, we have, this is not an order, by the way, this is my order of presenting these different models. So when I say third place, I mean the third here in my slide. So we have the more of temporal models, we have the LSTM, the long short-term memory, we have the transformer model, and all of these are neural network models, by the way, and they focus more on the sequence forecasting for flood prediction. For example, if you try to anticipate the rise of the water level within a river, LSTM gives a really good outputs because they are able to both learn the short-term pattern and the long-term pattern. So it's able to learn what happened within the last 5 hours, but also able to learn the entire pattern. So we have the spatiotemporal learning, which are these spatiotemporal models, they combine both the where and the when, and they are which actually enable more realistic modeling for floods, because we care both about where it's happening and when it's happening and how severe it will be. And the hybrid approach. The hybrid approach usually uses AI, and they usually use also physical informed constraint or model fusion, and they are very robust, and they generalize well from an area to a different area. So the right method depends on the data. So there isn't a right method to perform a flooding task, but it depends on the data, the time, the deployment, the person working on the project, and different other variables. So I created, actually, if I can go out of the search here. So I wanted to show a little bit of how these projects are actually created. So for example, I have, let me show you, I created a little bit of a platform here to show or to imitate a flooding scenario and how can it be. You're still able to see my screen, right? The new, window.
Yeah, we can see.
Yes.
That.
Yeah, okay. So if we look here, when we talk about caring where it will happen or the shape or the map, and we are caring, for example, it is happening within area. But when we talk about the prediction, we need to know how will it happen within the next 2 hours, and how severe or this will be, or to what extent it will be. And when we talked about the different inputs, for example, if you see here, depending on the soil saturation, and it's basically how much the soil can absorb from the rain, as long as it's hitting at the moment T, and later on when the water remains. And we can add here different variables, and all of these variables, they create these kind of platform or flooding model. So this model that I created here, it uses the area, so we need to specify in which area we are talking, or where we are trying to simulate the flooding. In the background, I have water level data, and I have soil, and I have I also defined how much I want to know in the future. And yeah, so I just wanted to use this as a let's say live demo as an example to saw how these models are created. If we go back to the presentation now. So I wanted also to mention a little bit of a case study that I worked on personally during my PhD. So the PhD I was working on what is the best model that I can use within an area to predict how much the river will rise within that area. And this is very, very important when trying to model flooding, because it actually influences from an area and a river to a river. There is a lot of variable to consider and to consider as an input to the model in order to be able to create accurate prediction. So the idea that I had here, it uses both, I was using both the water level data and the rain within the areas. So the idea is simple. How can we use AI, or how can we use certain algorithm in AI to be able to choose the right model to predict the levels within a certain, the levels of the water rise within a certain area. And this comes from the fact that if I go here, my first experiment I chose different location in Ireland, 70 actually station and location, and I'm trying to predict the rise within 1 hour in the future. And I end up with I tested different models, and I end up with different accuracy results. So the second one, I used the same model, but I extended the research area. And both of these experiments showed that I could not choose one general model to use to predict within all of the river. And this comes from the fact that these areas are different, the weight, the length, the soil type, the location, the drumlin, the different geographical characteristic of an area highly influence how the water behave within a river or within an area. So as I said, I used 12 models, and I used a baseline. And for my case, I used a linear regression model as my baseline. Then I tested different neural network models, and then I did a hyper or advanced model in order still to perform the same task. And I'm trying to find the best model that work overall. And the results were confirmed during the test and the training that there isn't a best model. And the idea here was to create a meta-learning approach or a hybrid approach to choose dynamically the model dependent on the input. So and this one was one case scenario. And the key takeaways here that I want to focus on is that AI can significantly enhance flood prediction and mapping when paired with strong data, especially strong data sets or strong inputs. We are able to understand and predict the pattern of the flooding and how it occurs, and it happened within different area. And scenario testing is really important. So when we talk about when we usually build flooding models, there is a second step involved when we test these models. So we imitate how the river can. Let's say we test a scenario when we put that the rain will be a continuous 48 hours of rain with a certain intensity in a certain area and all of that. So these scenarios, they will be able to test how good our model can perform. And yeah, so AI-enabled flood prediction and mapping holds significant promise, but we still suffer from a little bit of lack of the data, and which make it challenging to be precise about these type of events. I wanted to conclude my presentation of some of the most famous flooding events, let's say, in the Irish history, which are the Storm Babbitt in 2023, the winter of 2015 and 2016. And these both events, they were characterized by very long event rain with a very high intensity. Let's not forget about the 2009 floods. The first one, the Hurricane Charlie, was one of the extreme rainfall intensity, and I think it was over 3 days of continuous rain. And there were also one before that in the River Shannon floods. And this takes me to the end of my presentation, and happy to answer any question.
Asma, thank you very, very much. I personally found it very interesting, and I know there's a lot more detail that you could go into, but what I'd like to do is to invite people, Marion's got clapping hands there, invite people who have some queries to maybe unmute yourself and to maybe also show us visually who you are, but at least unmute yourself and ask your question. And I'm sure Asma will be very happy to answer. So any questions, anybody? I thought Dara McGovern was going to ask. Dara, have you got any comments or questions?
Hi, yeah, thanks very much, Asma. That was really interesting. I'm just curious, have you found any good methods to remove false positives from results that would be more similar to just waterlogged agricultural land, for instance?
Well, it depends actually on the decision of how to remove the false positive from a data set, so from an input, depends on the project. So it depends on the task that you want to perform. For example, if you want to model actually those particular rare events that happens, you will need to keep them because they will appear as a false positive in your data, but they are not. But if you're looking at just working on a certain, let's say, short-term flooding events or flooding that happen when it rains within 3 or 4 hours, you will better do the ablation and remove all of the other data sets. So this is not a one answer question. Actually, there isn't a best way to do or to remove the false positive, but I would say the testing and the way you model your methods, or you model, or you architect the models, highly influence the false positive.
Thank you. Thanks very much.
Okay. Anybody else? Don't hesitate. If you've got a comment or a question, please put it into the pot, and as I said before, Asma will respond.
Sandra.
Yeah, Sandra.
Hi, yes, yeah, very, very interesting, especially in light of the recent flooding we have. Do you know if the flooding predictor is in use at the moment by county councils or emergency services?
They do have, I'm not 100% sure, I don't have that, but I do know that they use the mapping, because if you go now and the OPW, you can see the flooding zones and where it's going to happen. And there is also the historical mapping of the floods. So you can actually download them, they are open source maps, and you can see where the flood happened and how it receded over time. So they do use flooding prediction and mapping, but I'm not 100% sure what kind of models they are using.
Okay, thank you.
Okay, Sandra, would you like to comment?
Sandra has just commented there.
Oh, sorry.
There's another question there from Nabil in the chat. So by any chance, Asma, do you know if there are plans to increase the number of river sensors to improve flood forecasting and early warning?
Well, I think they are working on it. So Meteorine and OPW, they're both, there is a lot of sensors right now, but I think it is within the future plans to increase the number of sensors. And they are actually quite a different research project happening all over the universities in Ireland, where they are implementing low-cost sensors. We had one a few years ago in DCU, and they were able to create a low-cost sensor that is able to actually capture the data within the river, and they did have a few test sites.
Okay, maybe I'll ask a question or two. Asma, the issue of the spatial resolution of the data that you input into your model. Now, I've worked in the past with engineers, and we've used very accurate, not satellite stuff. Like Sentinel is 10 meters by 10 meters, the kind of pixel size. But, the stuff that I've worked with engineers in the past with, I mean, it's like into the few centimeter type scale when we're modeling a particular stretch of river. Could you just maybe outline how the level of resolution, what's the implications of having high versus middle, low resolution imagery?
So usually in general, when we're talking about images, we are talking about computer vision models. And these models, they are highly affected by the resolution of the image or the input in general. So so when we talk about low spatial resolution, we mean each grid cell covers a larger area, right? So the small scale feature inside the cell are averaged out. So if you think about the picture, if you take it, when we talk about the resolution, it depends on how small that little grid we have within it, which it actually will influence how can we draw the border of that flood, or how accurate can it be. And when we talk about small rivers, we are talking about maybe missing these kind of border, or missing these kind of particular places, and they are kind of lost within the problem of the fact that the image is a low resolution image.
You see what I've got. Sorry, carry on, Asma.
No, go ahead.
What I was thinking of is drones. You know, you could get drones flying the rivers, particularly when the water level is low, and then you could get really accurate, high resolution profiles of the shape of the river course and the surrounding areas. So, a program of drone flying, certainly rivers that are likely to have a problem with flooding, that would be good. And if you're also doing drone flying, you could fly where there's been flood protection measures. So you could start taking them into account.
Well, when we talk about drones, there is a lot of other variables that we need to consider. So flying a drone is not as a simple task as it can be. First of all, you need to check whether that's legal or not, because you're not allowed to fly a drone anywhere. And usually when it's raining and when there is a high wind, like in Ireland, the drones are not able to fly accurately or capture the images. The other thing, there is protocols when we talk about involving drones in capturing images, and there is the huge not disturbing the wildlife, and the fact that the drones also needs to stay below 120 meters. So there is a lot of other variables to consider, not to mention that drones are very expensive, though they cannot be really a solution that it's implemented all over to get collect data. Yeah, if you think about it, about one particular case, let's say in a certain area, I'm flying a drone to capture there. But when we talk about modeling the flooding or any kind of time series related tasks, we want a lot of data. So that's why usually for flooding, satellite images are used. They're always there. There are a lot of them, and they're not impacted a lot. Well, they used to be highly impacted by the weather, but now they are better. So if we talk about 20 years ago or 25 years ago, the quality of the images, the satellite images, when it's cloudy very much, you cannot really use it because the resolution is very low. But now it's actually getting better. So I'm not sure about the drone. I cannot really know, but I know that there is a lot of other valuable to consider when we talk about drones and capturing images with the drone.
Okay. Any other comments, anybody? Please don't hesitate. If you've got some little idea or question tickling around in the back of your head, let's hear it. Asma, when I was mentioning... Okay,
yeah,
no,
just
carry on,
another
Asma.
thing I remembered for the flood. I don't know who asked about the flood, the models, whether they are implemented around or not. They are, yes, but I don't know which models, but they are also implemented at the catchment level. So at the a whole big area. So that's how they issue the public alerts, and that's how Materian is able to say, okay, this is it's red, or it's an orange alert, or it's a green alert. But how much data they use and how accurate is the background, I'm not sure.
Okay. Oh, excuse me. Asma, I was going to ask, when you're trying to do predictions, how do you take climate change into account?
Well, Bruce, in general, climate change is reflected on the data. So if you look at the rain behaviors in the 60s and the 70s and now, you'll find that it's not the same. If you look at the temperature, even within Ireland itself, the temperature highly changed. It increased significantly in Ireland compared to 40 or 50 years ago. So you can actually detect the impact of the trace of climate change within the different data sets, and these data and all of those patterns are captured by the model.
Okay, so in other words, yeah. And you then kind of predicting that the flooding into the future through climate change, the past would be a reasonable reflection of the trend that's likely to continue. That's basically, I think, what you're saying.
Yeah.
Yeah. Okay.
Exactly. I think there is a question in the
chat.
Chat.
Yeah. What is the minimal temporal baseline between two satellite images for you to make a time series, and what type of image you used in your study? Well, for the project that I showed today, I did not use image input. It was mostly time series data sets, but in general, there is no single universal minimal temporal baseline. It depends on the flooding task, and it depends on the sensor types. So, for example, I don't know, out of my head, if you want to do a time series task, it requires at least 4 to 8 images, let's say. And well, these tasks, it depends. There isn't really a minimum baseline to use. I don't know if I answered the questions or not, but it highly depends on the task. But in terms of data, the more the better, always.
Okay.
That's how I believe, and I think most of people working with these different models, the more data, if you think about it, the more data I have, the more pattern I can extract, the more similar pattern I can detect from my data, the more I can accurately predict if I have the same variables in the future.
Yeah. And AI neural networks are good at picking up patterns in data.
Oh, yes.
Whether it's temporal or spatial. That's correct, Asma?
Yes, that's very correct. Neural networks, models in general, and AI models, the strength comes from the fact that they can pick up these patterns both in the short term and in the long term, which is very, very important when we are trying to model how, because the inputs usually flooding, there is many variables that affects this the flooding events. The infrastructure, for example, is a big factor, and the drainage systems, and there is many other new research, for example, that they are looking at different alternative. I don't know if you all heard about the sponge area. So, for example, there is the idea of building a sponge area where we redirect all of the water flooding in the, for example, in motorways to a certain area where it can absorb it. I mean, when we talk about it, it will be like a park. So there it can absorb all of that water at once, and it will actually solve the fact that the drainage system at a certain level, they do function nicely, but at a certain level they are saturated. So, but there is also other side to that it's very hard to model and to build these sponge areas, because it's not like you're dumping all of that water in an area, but it should be useful. So the soil type and all of the different variable of that area is very important, because certain soils, as you know, they absorb much more on the surface, and on the ground that they store much more to other type of soil, for example.
In planning, town and regional planning, there's something called SUDS, S-U-D-S, which is a whole framework, a whole set of ideas as to how to deal with flooding and stormwater in a more sustainable kind of way. And I mean, I personally have designed housing layouts and things, and I've provided for those sponge areas that you're talking about. But, you know, I come back a few years later and the municipality hasn't done anything that they meant to do to keep those sponges working in the way that they could or should work. So, you know, it's, I don't know, you know, you can get part of the way there, but it also requires other inputs by other entities to keep it all working fine. So,
yeah.
That's just my experience.
I do agree.
Not always good.
Sponge, maintaining the sponge area is not an easy task.
Anyway, sorry, is there, for good prediction, is there anybody else who would like to comment? Otherwise, I think we've pretty much come to the end.
There's a question there in the chat from Anastasia there.
Okay, you mentioned that during your PhD experience. Oh, yes. So the strongest ones were actually LSTM, but wasn't, I was expecting that, because LSTM, or long short-term memory, they are very good at detecting patterns, and small and big patterns, as I mentioned. So they were working great in certain area, but they were working great, for example, in Dublin. When we talk about Galway, they weren't performing as good, because in Galway, as you all know, the rain doesn't stop. The intensity is not big, but we have longer rain events with low intensity. In Dublin, we have a lot of rain at once, but then it stops. So in Galway, LSTM wasn't doing as great as in Dublin. And then I start noticing that in different other areas, it depends. Sometimes linear model were the best, sometimes, but mainly neural networks models are great. But I came at a point, and for my experience in my PhD, when I started, I thought I will be able to find the best model to predict the water level. Towards my second and third year, I start making the peace with the fact that there isn't a single best model, and I need to look into different approach. And then when I decided to go with a meta-learning approach, I don't know if you're all familiar with meta-learning, but meta-learning is the way that you teach your algorithm, learn how to learn. So I taught the algorithm how to detect the model depending on the area. So in another way, I was telling it, look where you are and find the best model that fits those characteristics. So if we are talking about wide river with a high depth, which is, there is dumpling there, and there is a certain type of soil. So I used a lot of data sets, as I put, and there is different climate and temperatures there. Use this model. This model is the best within that area. So that's the whole idea of my PhD experiment in general.
Okay, I think there's another comment here. Dorman?
In South Africa, yeah, I do agree with that, Dorman. I come myself from Tunisia, so I'm North Africa, and I know, for example, that in our country, there isn't enough sensors deployed within the river. Currently, I'm also involved with the World Meteorological Organization, and the task that I'm on is actually we're trying to make a metadata for the different water level data sets that exist within the world. And what I'm noticing, and we're all noticing, that when we talk about Ireland or Europe or different countries, you find a lot of sensors. So 300 and 500 or 600 across a country is a lot of sensors. And when we talk about, I don't know, North Africa and South Africa, we barely talk about 2 or 3 or 4 sensors implemented along a big, huge river, which makes it very hard to really it's really hard to model and anticipate. Currently in Tunisia, for example, there were flooding, and then the past 3 days in the capital, people weren't going to school because all the roads were flooded, the housing, and it's a really huge problem. So yeah, and that comes also from the fact that we don't have sensors, we don't have data, we can't build models, we cannot anticipate what will happen, and we do not know what to do or the next task. So yeah, I 100% agree with you.
Okay, I see there's another chat comment coming in. While the typing is going on, Asma, did you have a LLM front end where the user could just speak into your model and, you know, it would do what it needs to do?
Speak. Can you elaborate on speak to my model? I mean, interpret my model?
Yeah, you know, like ordinary citizens could speak into the model using ChatGPT, you know, or one of these chat facilities.
I mean, to ask questions regarding what will happen or what's happening, because, you know, when we talk about LLM, it depends on what's the use of the LLM. For example, myself, I'm working on to integrate an LLM to my models now, but I want them to be able to interpret my results, not interfere with the model itself. But mostly when I say, okay, I had 80% prediction in this area that a flood will happen. That is when we talk about normal users or normal people, such or let's say non-tech people, 80% accuracy doesn't really give the extended meanings. So I'm looking at how can we integrate LLM in order to best present the results to a certain audience, which is a non-tech audience. Yeah.
Okay. All right. I think we've probably come to the end of the Q&A session. Marion is just typing, so I see. So maybe we could wait for Marion. Marion's saying thank you. I think, Asma, on behalf of everyone who's participated, I think it's been an excellent, very, very clear presentation. And I think this recording of this webinar should be made more widely available. And in that regard, I will certainly try and see that it can be made available through the IRLOGI, the European Umbrella Organization for Geographic Information. So it's not just the people around the table, as it were, but I think there will be a much wider audience who will benefit from your insightful and wise words. Asma, thank you very much.
Thank you, Bruce. Thank you for having me. I hope I managed to answer your questions. And feel free to contact me anytime you like. I'm available by email, my DCU or my Insight email. And thank you for having me in this. And yeah.
Absolute pleasure.
Thanks, everybody.
Thank you.